You've probably heard of dark matter, and may even have been taught about it in school. It makes up a large chunk of our standard model of astrophysics, despite never having been seen or directly detected. The 50-year, multi-billion-dollar search for this elusive form of matter continues to this day. So, what is dark matter, and why haven't we been able to see it yet? If we can't see it, how do we know it is really there? Furthermore, how can something that's never been proven have such a place in the science you find in the textbooks? And after so many decades of fruitless searching, is it time to embrace alternative ideas? These are the questions we shall be aiming to answer as we peel back the layers of the dark matter mystery. What is dark matter? Dark matter is a theoretical form of mass which has never been detected directly, but is inferred to be present in space due to its gravitational influence on galaxies. Proponents of the theory claim it to be some kind of undiscovered elementary particle, but one with properties that do not fit with our relatively rigorous standard model of particle physics. Dark matter's most mysterious property, responsible for its decades of non-detection, is that it seems to be electromagnetically neutral. It does not appear to interact with the electromagnetic force in any way, and thus does not absorb, emit, or reflect light, or any kind of radiation in fact. This renders the particles completely invisible, and not known as dark because of any actual color. In fact, a better way of describing it would be missing Massachusetts. No matter how hard we look for it, it evades the many eyes of our electromagnetic observatories, even the beasts such as Hubble and James Webb. However, scientists are confident that it exists, or that something exists in its place at the very least, because without a substantial source of missing mass, the present-day layout and structure of the universe would simply not be possible. When we run simulations aimed at recreating the universe's life, from the moment of the Big Bang, none of them are able to give rise to the complexity we see today, with only the gravity of visible, baryonic matter, i.e., the gravity of galaxies and their stars and gas. While galaxies themselves are massive, space is incomparably more enormous, and even the gravity of all the universe's galaxies combined falls significantly short of the influence necessary to explain how the cosmos ended up looking like it does today. At least 5/6 ts of the gravity-inducing mass needed to explain galaxy clusters is missing, and thus most scientists agree that the majority of the universe's mass must be in this dark form which we cannot see. However, this mass still exerts a gravitational influence, which affects the space around it in a way which we can see, but not directly enough to unequivocally prove dark matter's existence. The idea that the universe's contents contain more than its visible matter has been speculated upon for centuries, but scientists didn't really start to properly embrace it until the 20th century. From the 1920s, a few astronomers suggested the existence of invisible mass based on the observed motions of stars within our galaxy. But it wasn't until the 1930s that we began detecting tangible signs of missing matter. Signs of missing mass. In 1933, Swiss physicist Fritz Zwicky plotted the redshift of galaxies within the Coma cluster, a group of more than 1,000 galaxies lying 330 million light-years away, seeking to map the movements of the galaxies within. By applying virial theorem to his observations, he determined that the cluster would need around 100 times more mass to keep its galaxies locked in the formation he was observing, with the gravity of the just stars in these galaxies nowhere near substantial enough to bind the cluster. Zwicky concluded that the Coma cluster must contain a significant amount of hidden mass, coining the missing mass problem, the first step down the dark matter rabbit hole. In the following 40 years, little progress was made in understanding the nature of missing mass. But moving into the 1970s, a second crucial line of indirect evidence for its existence was detected. In 1970, physicists Vera Rubin and Kent Ford mapped the sprawling spiral arms of the Milky Way and Andromeda galaxies by plotting the velocities of each stars as they orbited their respective galactic cores, with particular interest in those stars on the outskirts of the two galaxies, where gravity should be much weaker. Newton's laws of gravity tell us that its strength decays proportionally with distance from the object exerting an influence, and so ordinarily, stars on the outside of a galaxy should be orbiting slower than those on the inside nearer the galactic core. Our solar system exhibits this pattern of behavior with its planets around the Sun. But instead, Rubin and Ford found that stars on the outskirts of both galaxies seem to orbit at the same speed as the stars further in, some even faster, in fact. But this should mean that both galaxies ejected their stars and flung themselves out of existence long ago if their cores were the only thing binding their structure. Assuming Newton's laws actually apply to galaxies, the fact that the Milky Way, Andromeda, and many other spiral galaxies have spun at these speeds and remained bound for billions of years suggests that there is another source of load-bearing mass enabling their structure. Once again, we had stumbled upon indirect evidence of missing, invisible mass. The work of Rubin, Ford, and many others culminated in an influential 1983 paper discussing the missing mass problem with a focus on galaxy rotation, and it predicted that this hidden mass must far outweigh visible matter by a ratio of 6-to-1, an estimate we still go by to this day. This means that, whatever the missing mass is, it must account for more than 85% of the universe's matter, despite being in a form that renders it invisible. Fast forward another 40-odd years, and we're still not much closer to seeing the dark matter particle. Every effort so far has proven largely unsuccessful, but scientists have only become more certain of its existence during that time, due to the number of emerging indirect lines of evidence. As mentioned, we can infer the presence of dark matter due to its gravitational influence on the visible matter surrounding it, which creates a number of indirect effects that can be used to constrain certain properties. This understanding is applied in the lambda-cold dark matter model, or lambda-cdm. Currently, it is our most complete, well-regarded, and widely accepted scientific description of the universe and constitutes the science you find in textbooks. It ties together a number of different theories and frameworks, such as the Big Bang, general relativity, and the Standard Model of particles, into one comprehensive, complete theory. It's not without its gaps, but it is nonetheless the best model we have for concurrently explaining many of the universe's properties under the same umbrella. The lambda-cdm holds dark matter as one of its key concepts, describing it to encompass around 85% of all the universe's mass, and just under a third of all the stuff in existence. It describes the particle as cold, but this notion of temperature actually refers to the amount of energy the dark matter has. For example, hot dark matter would mean energetic dark matter, capable of streaming at very high, even relativistic velocities. This would give dark matter particles a large free streaming length, with profoundly different implications for the galaxy clusters of the universe. If dark matter were hot, then the universe's early ocean of particles which permeated all of space would have given rise to colossal intergalactic structures early on, which separated into smaller clusters over time. A top-down approach to building a universe. But our observations of the very deep universe dispute this. The earliest galaxies were small, immature ones, with larger galaxies and then clusters coming later on. Thus, the universe's dark matter cannot be hot and must instead be cold, with a low free streaming length, which is therefore slow-moving. A trait which favors a bottom-up approach to sculpting the cosmos, starting with the subatomic particles created by the Big Bang. Dark matter in the early universe. The lambda-cdm holds the Big Bang at the center of its assertions, the theory that the universe began from a small, singularity-like point of infinite heat around 13.8 billion years ago. For an unknown reason, this point began to expand, and its suddenly finite temperature has been falling ever since. As the contents of the universe were able to breathe for the first time, things started to happen, and, in the 20 minutes that followed the birth of the universe, subatomic elementary particles had condensed. Dark matter is thought to have been among these primordial elementary particles, but its role in the events of the very early universe is unclear. But what we do know is that, for about 380,000 years after the universe was born, its baryonic, visible contents existed in a plasma state, an enormous, energized, omnipresent ocean of intertwined particles. At temperatures this high, particles of both light and matter would have been interacting, as photons struck, bounced off, and were absorbed by ionized atomic nuclei. This, in turn, would have accelerated the matter particles to relativistic velocities, giving them a large free streaming length. This would have washed out any density fluctuations in the homogeneous plasma up until it turned to atoms during the epoch of recombination. Once the plasma ocean fell below the 3000 Kelvin threshold needed to maintain its state, It was harvested all over the universe to create the first neutral hydrogen and helium atoms, as electrons latched onto exposed atomic nuclei. But, if not for dark matter, these atoms would have been spread totally smoothly across space, with no mass density perturbances. However, we do see evidence of perturbances in both the CMB and the arrangement of galaxies. This is because dark matter had already begun to interact gravitationally long before recombination, and thus the distribution of atoms mimicked the distribution of dark matter at that moment. This resulted in some areas of space with greater concentrations of atoms, better suited to the buildup of the universe's first star-forming gas. And so, within only about 200 million years or so, the first stars ignited from this primordial hydrogen gas, illuminating the dark, cavernous cosmos left behind by recombination. Dark matter filaments. During these 200 million years of darkness preceding the first stars, the universe's primordial dark matter particles would have continued interacting gravitationally, condensing to form the first dark matter structures, much sooner than the first stars. In addition to its head start on recombination, dark matter is believed to condense faster than baryonic matter, as its electromagnetic neutrality means it is not slowed down by the radiation pressure of photons. However, this also probably means that the dark matter particle lacks the full range of interactions necessary to condense into coherent, solid bodies. Normal matter, like gas, loses energy as it condenses, as atoms feel drag force and photon pressure. This lost energy manifests as reduced momentum, which would otherwise maintain the distance between atoms. But instead, they draw nearer and nearer, and until they undergo a gravitational collapse. Dark matter, on the other hand, lacks an efficient means to lose this energy, and so is probably not capable of collapsing with other dark matter particles. And so, while dark matter did concentrate faster than atoms during the Dark Ages, it stopped short of forming any solid structures, like dark matter stars or planets, and instead collected into a sponge-like network of enormous but diffuse dark matter branches, or filaments, which line the entire universe. These dark matter filaments still exist today, linking up to form the largest thing in existence, the skeleton of the universe upon which all galaxies reside today, the cosmic web. The massive arms of this dark matter structure amplified the density disparities of the early universe by acting as a gravitational well. Star-forming gas accrued along these filaments, much faster than would have been possible given the gravity of the gas alone. And because the universe's baryonic contents exist almost exclusively along these branches, we can think of the universe's galaxies as the skin to its underlying dark matter skeleton. After the cosmic web formed, the dark matter contained within continued to condense, contracting into smaller, more compact, but still relatively diffuse bubbles or halos. These halos are thought to have acted as the spawning grounds for the first galaxies, as baryonic matter concentrated within their cores. This led to rapid accumulation of stars and gas into the first gravitationally bound dwarf galaxies, only 100 million years after the cosmic dawn. And it is the gravity of these halos that is thought to enable the anomalously fast galaxy rotation observed by Vera Rubin. While most galaxies lie at the center of one of these dark matter halos, their outer rims are believed to act as a gravitational wall, which binds the galaxy together from the outside, which would explain why fast-moving outlying stars are not ejected. It also suggests that the majority of the binding work in a galaxy is done by these dark matter halos, and not by the nucleus of the galaxy, as we once thought. Around 500 million years after the first galaxies took shape, they were merging, attracting their near neighbors and combining their stars, central black holes, and probably their dark matter halos. And in the 13 billion years since, these galaxies have continued to grow and have linked up with other galaxies along their dark matter filaments, propagating as huge galaxy clusters spanning millions of light years. None of this, the dynamics of galaxy clusters, the rotations of the Milky Way and other spiral galaxies, nor the distribution patterns we see on the CMB, would have been possible without dark matter as described by lambda-cdm, were it not for the cold, heavy dark matter particles shifting around in the early universe. Density gradients of the scale we see just wouldn't have been possible. The universe's contents would have been homogeneous until recombination, and its atoms would have slowly condensed into completely randomly distributed galaxies. But instead, we see a universe partitioned by its skeleton, a backbone of mass which enables interactions on macro-universal scales. And, though we've never seen this skeleton directly, we can observe its effects as influences the clusters that line it today. In fact, galaxy clusters are the ideal environment to search for dark matter, as we can infer its presence via three separate means. 1. From the velocity distributions and motions of its galaxies. 2. From the cluster's X-ray spectrum. And 3. From the warping effect a cluster's mass has on light passing through it. The best examples of evidence for all three can be found in the Bullet cluster of galaxies, located 3 billion light-years away in the constellation of Carina. This peculiar galactic structure is actually the product of two clusters in the aftermath of a collision that took place around 150 million years ago. The smaller, subcluster appears to be moving away from the larger cluster, surrounded by a prominent bow of shock, suggesting an infall and pass-through, which is what is referred to by the bullet part. The structure, speed, and scale of interactions within this cluster cannot be explained by the mass of its constituent galaxies alone, not least because the cluster's gravitational focal point appears offset from the centroid of its galaxies. Dark matter theorists have an easy time explaining this discrepancy, whereas alternative theories struggle. Then you have the cluster's X-ray spectrum, and just as the gravitational focal point is offset from the galaxy's center, so too is its X-ray peak. The Bullet cluster is one of the hottest and most X-ray luminous clusters we know of, and its emissions profile also cannot be explained by baryonic gravity alone. These X-ray signatures are caused by gas within the two clusters, which is becoming heated and energized by the drag force of gravitational influences as it migrates. But the Bullet cluster's spectrum suggests its gas is under much more of an influence than could be exerted by its galaxies. The X-ray emissions are unusually prominent and also slow-moving, which implies they are under a lot of drag pressure from a gravitational influence that is not nearly explainable by the galaxies themselves. These X-ray emissions gave us our strongest indications yet of the existence of dark matter in the Bullet when they were detected by NASA's Chandra telescope in 2007. In the years since, we have observed our third line of evidence for dark matter in the Bullet cluster as well, gravitational lensing. This phenomenon occurs when space-time, as described by Einstein, is curved by the presence of large volumes of mass. This causes any photons of light passing by that object to have their straight paths curved as they stream through warped space-time. Then, when these photons reach the Earth and are detected, the light arrives distorted in the shape of a lens around whatever is exerting the influence. This effect was predicted by Einstein and was recently pictured in the James Webb Telescope's first-ever image of the SMACS 0723 cluster. But the thing is, sometimes we see light passing through supposedly empty space in galaxy clusters, which still arrives lensed, in a way that cannot be explained by the gravity of galaxies alone. In the case of the Bullet cluster, lensing has been observed in two prominent regions independent of the centroid of its galaxies. This gave us yet another strong indication of the existence of invisible, missing mass within the Bullet cluster. And by surveying other clusters for similar lensing effects, we can get a practical sense of the distribution of dark matter in space, creating this image. It shows a distribution that is broadly similar to the anisotropies of the CMB, thus providing corroborating lines of evidence for dark matter's existence as we understand it. So, with these indirect lines of evidence considered, what properties can we actually deduce about the form of the dark matter particle? Well, as mentioned, scientists believe it to be a new kind of elementary particle, that is, one which cannot be broken down into any further substructures, like a quark, but much heavier. The abundance of dark matter mass and its distribution suggest a large, heavy, non-relativistic particle, with a mass 10 to 100 times greater than a proton. And though this neutral particle doesn't appear to interact with light, scientists believe that it should have some level of interaction with ordinary matter, just a very negligible rate of interaction, far too subtle for us to detect with current technology. The placeholder name we give to this elusive particle is the Weakly Interacting Massive Particle, or WIMP, and it is these WIMPs that are the target of our relentless search for dark matter. If dark matter really functions as we understand it, whereby galaxies form within the most dark matter-dense areas, then we should be residing within an area of enhanced dark matter right now. As such, there should be trillions upon trillions of these invisible particles streaming through all parts of the Earth every single second. Hinged on the assumption that these particles do weakly interact with normal matter to some degree, our experiments so far have aimed to isolate the precise, rare set of circumstances under which this might happen, but most of the time, we are limited to detecting indirect evidence. A direct detection of dark matter would involve detecting the energy released by a WIMP as it collides with an atom. As it strikes the nucleus, this may cause a recoil that releases the energy in the form of either scintillation light or excitations within a crystal. To detect scintillation light, direct detection experiments use noble liquids like xenon, Xe, and argon, Ar, deep below the Earth's surface. Examples include xenon 1T, Lux, DAP, warp, darkside, Panda-X, and ARDM. In contrast, other experiments seek to detect excitations within crystals, using elements like germanium, G. Examples include super-CDMS, CRESSD, Edelweiss, and Eureka. So far, however, neither type of experiment has yielded any signs of weakly interacting missing particles. Generally, for a particle that doesn't want to make itself known, we are better off searching for indirect evidence, primarily because there are more avenues we can explore to achieve it. We can use existing particle collision experiments, such as the Large Hadron Collider, to try and create dark matter. While the products would immediately escape the collider's environment, we would be able to indirectly infer properties about the invisible matter created, based on the amount of energy apparently missing from the exchange. But that sounds a lot like expensive shadow chasing. Thankfully, there are other indirect detection methods which are slightly more promising. As known by the Standard Model, all particles have an equivalent antiparticle, another particle with the same mass, but opposite electrical charge. For example, the negatively charged electron has the positively charged positron. And when pairs of particle and antiparticle come together, they latch onto one another and cancel each other out. This is known as an annihilation, and it converts the particles' masses into high-energy gamma-ray photons. Unfortunately, dark matter is thought to be neutral, and so it won't have an equivalent anti-dark matter pairing. However, if dark matter particles can act as their own annihilators, then the resulting interaction may produce similar characteristic gamma-ray emissions. And so, gamma-ray observatories, both past and present, have been used to search for these types of signals. To have the best chance, they probe the heart of the Milky Way galaxy, where the highest localized concentrations of dark matter are thought to exist. But given the sheer number of potential gamma-ray emitting sources from within the galactic core, isolating one indicative of dark matter is a needle within a cosmic haystack of a task. However, there have been some candidate signals proposed. In particular, the galactic center excess, a persisting gamma-ray surplus emanating from the Milky Way's central bulge. The signal cannot be explained via any conventional gamma-ray sources, and may be indicative of an especially high volume of matter-to-dark matter interactions within the bulge. The recently launched James Webb Telescope, which has a field of view capable of reaching the center of the Milky Way, will allow us to gain the most comprehensive dataset yet of the galactic center excess. So, we may see further confirmation of dark matter's role in the Milky Way's central bulge within our lifetimes. Similarly, positrons produced by dark matter annihilations in the core would be energetic enough to break free, in which case they might reach us as high-energy cosmic rays. And an excess in the flux of high-energy positrons reaching us from space was observed in 2008 by the Pamela probe. This excess could similarly be attributed to other explanations, and as always, requires corroboration from other lines of evidence. However, it is suggestive of potential dark matter annihilation events in the Milky Way's core. Searching for dark matter annihilation signals in other galaxies or galaxy clusters, where the mix of possible emitting sources is less dense, would also increase the reliability of any detected signals. If dark matter is out there, a combination of these indirect detection methods will eventually lead us to it. So, the case for dark matter is a multifaceted one, with supporting evidence emerging from multiple disciplines and strands of observation. In essence, the collision between the two galaxy clusters in the Bullet cluster appears to have separated ordinary matter from dark matter. This gave rise to a visible offset between the center of mass, as inferred from gravitational lensing, and the distribution of hot gas, as inferred from X-ray measurements. Such observations serve as a critical test for the presence of dark matter, and no competing theory has yet managed to replicate the breadth of dark matter's influence, as predicted by lambda-cdm. In conclusion, while we are yet to directly detect dark matter, a preponderance of indirect evidence supports its existence, from its influence in the dynamics of galaxy clusters and rotation curves, to its potential presence in cosmic ray and gamma-ray signals. The advances made in the decades since Vera Rubin's initial discovery have helped to further constrain the properties of this elusive component of the universe, and the search for dark matter is set to continue apace, with future missions seeking further clarification on its fundamental nature.